Hello everyone. So today we are discussing about a theorem 3.9.1. If x naught is an arbitrary point of the given differential equation, that is p of x into y double dash plus q of x into y dash plus r of x into y is equal to 0. That is, if p of x is equal to q of x divided by p of x and q of x is equal to r of x by p of x are analytic at x naught, then the general solution of the above differential equation is y is equal to summation over n is equal to 0 to infinity an into x minus x naught all raised to n, which is equal to a naught into y1 of x plus a1 into y2 of x, where a0 and a1 are arbitrary and y1 and y2 are two power series solutions that are analytic at the point x0. The solutions y1 and y2 from a fundamental set of solutions. Further, the radius of convergence for each of the series solution y1 and y2 is at least as large as the minimum of the radii of convergence of the series for p and q. So here this theorem is discussing about the power series, and here is mentioned about the y1 and y2, which are fundamental set of solutions, and they have the general form, that is y1 of x is equal to 1 plus b2 into x minus x naught the all square plus etc, and y2 of x is equal to x minus x naught plus c2 into x minus x naught the whole square plus c2 into x minus x naught the whole cube plus etc, where b2 plus c2 is equal to a2. Hence, y1 satisfy the initial conditions, that is y1 of x naught is equal to 1 and y1 dash of x naught is equal to 0. And also y2 satisfy the initial conditions, that is y2 of x naught is equal to 0 and y2 dash of x naught is equal to 1. Thus, w of y1 y2 of x naught is equal to 1 and which is not is equal to 0. According to the previous theorem, the radius of convergence of the series solution cannot be less than the smaller of the radii of convergence of the series for p and q. To determine the radii of convergence of series for P and Q can be done either of two ways. One possibility is to compute the power series for P and Q, then to determine the radii of convergence by using one convergence test for infinite series, whatever you can use. However, there is an easier way when p of x and q of x and r of x are polynomials. Okay, and it is shown in the theory of functions of a complex variable that the ratio of the two polynomials, say q of x divided by p of x, has a convergent power series expansion about a point x is equal to x naught if p of x naught is not equal to 0. Further, if we assume that the factors common to q of x and p of x have been cancelled, then the radius of convergence of the power series for x, q of x divided by p of x about the point x naught is precisely distance from x naught to the nearest 0 of p of x. In determining this distance, we must remember that p of x is equal to 0 may have the complex roots, and these must also be considered. For example, consider the Airy equation, that is y double dash minus xy is equal to 0, given in worked out problem 5. For this equation, p of x is equal to 1 and q of x is equal to 0. R of x is equal to minus x are polynomials. Here p of x is equal to q of x divided by p of x, and which is equal to 0, and q of x is equal to r of x divided by p of x, which is equal to minus x. Since p of x is equal to 1 and which is not equal to 0 for every value of x, power series for both p and q converges everywhere. Hence, by our theorem, the series of solution of this equation about any point converges for all values of x. A series solution may converge for a wider range of x than indicated by our theorem. So the theorem actually gives only a lower bound of the radius of convergence of the series solutions. For example, consider the legendary equation, that is 1 minus x square into y double dash minus 2xy dash plus alpha into alpha plus 1 into y equal to 0, given in worked out problem 2. For this equation, p of x is equal to 1 minus x square and q of x is equal to minus 2x and r of x is equal to minus alpha into alpha plus 1 are all polynomials where p of x is equal to 0 and x is equal to 1 or x is equal to minus 1, and these points are at distance 1 from x equal to 0. Hence, a series of solution of the differential equation about the point 0 converges at least for mod x less than 1 and possibly for large values of x. Indeed, it can be shown that if alpha is a positive integer, one of the series of solution after a finite number of terms, that is, one solution is a polynomial and hence converges not just for mod x less than 1 but for all x. For example, if alpha is equal to 1, the polynomial solution is y equal to x. So this is about this theorem. So thank you.